Hi everybody, let's go over a problem from 3.2. We're going to solve the polynomial 2x to the fourth plus 13x cubed plus 29x squared plus 27x plus 9 equals to 0. We'll also just write it in factored form. So the process that we're going to go through is just to always just be in the habit of identifying how many real zeros we have. And if we're asking for real zeros, since it's a degree 4 polynomial, we're going to say that there's at most 4 real zeros. We'll do the Descartes rule of signs, and you don't always have to do this one. I'm not going to require it on the exam or anything. I'm just purely using this as something else you can do to help narrow down the rational zeros theorem process to eliminate some of the potential zeros. And so you can always just get in the habit of doing it in your head and not necessarily writing everything out. We'll then go ahead and do the rational zeros theorem, and then we'll test for our zeros. And once we get our zeros, we can write it in that factored form. Alright, so we know that we have since it's a degree 4 polynomial, that we're going to have at most 4 real zeros. Lost some of my words right in the factored form. So at most 4 real zeros. I'm testing out a new feature. I'm in the Google Drawing, so it seems like it's a little smoother. So we'll have at most 4 zeros, and then when we look at Descartes, to find the positive real zeros, we're going to note the number of sign changes that the polynomial has. And since everything's positive, there's 0 sign changes. Which means we have 0, which implies we have 0. Let's make this a little neater. Which implies we have 0 positive real zeros. Okay, so to determine the number of negative real zeros, we're going to find f of negative x, and so our polynomial is this, and so when we plug in negative x everywhere, all those odd degrees are going to change to this negative. So we'll have 2x to the fourth minus 13x cubed plus 29x squared minus 27x plus 9. So this was f of negative x. And now we start to have some sign changes. We have one here, one here, one here, and one here. So the sign changes are when it goes from positive to negative or negative to positive. And so in this case, there's 4 sign changes. Which means we'll have 4 negative, let's do it this way. We'll have 4, 2, or 0 negative real zeros. And so, well, it could be in parentheses as well. So there's 4, 2, or 0 negative real zeros. Alright, so here's that benefit of just doing Descartes, even kind of in your head, is when we go to the rational zeros theorem, I'm still going to write plus or minus just out of habit, but when we go to that next step to test those zeros, I'm not going to test any positive ones, I'm just going to stick with negative zeros. Okay, so let's cut and paste all this, or delete all this, and let's look at the rational zeros theorem. So I just am abbreviating it as RZT. And so we note that all the coefficients of our polynomial are integers, so we can use the rational zeros theorem. My P is 9, and I want to list all the factors of 9, and I'm still going to do it plus or minus. So plus or minus 1, plus or minus 3, and plus or minus 9. My Q is 2, and I list all the factors of 2, which is plus or minus 1 and plus or minus 2. You can see why the coefficients for the rational zeros theorem have to be integers, because we're basing P and Q off the fact that its factors are just integers as well. Okay, so when we look at the ratio of P over Q, I'm going to have plus or minus 1, plus or minus 3, plus or minus 9 all over 1. So I'll have all of these. And then I'll have all of these divided by 2. So plus or minus 1/2, plus or minus 3/2, plus or minus 9/2. So these are all my potential real zeros, or all my potential rational zeros. And we know there's not going to be any positive ones. And so in the prior videos, Professor Sullivan was using the remainder theorem, that is finding f of -1 and seeing is that 0, and proceeding along the way, because if you know that when you plug in the 0, a potential 0 into the function and you get 0, then that 0 must be one of the factors. And so another way we can do this is just go straight to synthetic division. I don't really care which process you use. And so I'm going to actually stop the video here and make sure I just have enough time to finish this. So we'll go ahead and pick up with the testing over potential rational zeros.